Good morning. Today I will talk about this presentation with title A New Class of Galerkin Expansion Models for the Study of Thermoacoustic Instabilities. This work was carried out in conjunction with Wolfgang Polifke. So the one who talks right now is Camilo Silva. So let's start with the Helmholtz equation and consider a case when we have no flame. So basically, we are interested in the cavity acoustics of the system. So in here, we have the acoustic modes that we call passive acoustic modes. We have the speed of sound that can change in a space, and also we have the so-called passive acoustic eigenfrequencies of a given mode K, who in turn are related with a growth rate and a frequency of oscillation. Okay, imagine we solve the problem, which is actually just solving an eigenvalue problem, and we obtain many different eigenfrequencies, so many different cavity modes. But in here, we only talk about the first two, and we call it S1 and S2, with the corresponding growth rate and frequency. Okay? Now, we do the exercise and we say, okay, what happens if we introduce the flame, a given flame? So we will solve again the problem. It's going to be an eigenvalue problem, perhaps very nonlinear depending on the flame model. And then we solve the eigenvalue problem and we can obtain something like this. So we can have, if the flame is not strong, at least we can have like eigenfrequencies that are close to the ones which are the cavity acoustic modes, but perturbed. So we will call this perturbed acoustic mode because this is just moved or drifted because the flame is now present. Okay. In addition to that, we have something called intrinsic thermoacoustic mode, which is not related to the passive acoustic modes of the system, so to the cavity acoustic modes. And this is understood as following. So we have a velocity perturbation that generates an acoustic wave or a flow modulation that perturbs the flame, and therefore we have unsteady heat release rate. These heat release rate fluctuations will produce acoustic waves, and one is gonna just move upstream and will modulate again the flow, closing thereby the loop. Okay, so this is what we call intrinsic thermoacoustic mode. So the thermoacoustic spectrum of an active thermoacoustic problem consists of perturbed acoustic modes and intrinsic thermoacoustic modes. Well, many situations is somehow non-convenient to solve this active problem many times. For example, when you have many different flame models, or you want to do parametric variations, or even if you want to understand the physics of the problem, somehow this could be at some point a black box model. So that's why this so-called Galerkin expansion becomes interesting, because the idea is to develop a very like a reduced order model that mimics under some conditions the results of the active problem. So how does it look like? We first start with the active problem, but now we will have this active acoustic mode expressed as a linear combination of the passive acoustic modes. Okay? In this presentation, we talk about something called one mode expansion, which means we just care about what happens very close to a given eigenfrequency, and therefore we think one mode is sufficient to describe what we want to study. Afterwards, we just project the corresponding expression to the passive acoustic mode again. Okay? So this is almost the final expression, but we need something else which is quite important, is how we relate or how we introduce the flame transfer function. Here the heat release is just produced by a given input of the upstream velocity multiplied by the flame response. Okay? If you see here, we talk only about pressure. Pressure, pressure, pressure. How can I get a velocity into the expression? Basically, we need somehow a function that gives me pressure and velocity related. And this is done most of the time with a so-called acoustic impedance that is calculated or measured at the particular frequency of interest. Okay? Once I do this kind of calculation, and this is shown in the paper, I will have this expression, and this is the so-called one-mode expansion. This is not new. It has been already developed in thermoacoustics by Kulik and also exploited in the research of the group of Nicolas Noiret. Okay, so basically what we have done so far is that this model, which is somehow complex, is rich, can be expressed as a one-mode Galerkin expansion, which is nothing but an algebraic equation. And I expect, or we expect, that this one describes very well what happens in this one in a certain set of conditions, like for example, a region of eigenfrequencies in the complex plane. Normally, we expect the following. We expect that this is gonna work well if the drift, so if S is not far away from S1. So basically, if the heat release rate is small. Under such conditions, I will expect that this model retrieves very well the actual reference result, which is the one of the active eigenvalue problem. Okay. Well, so I expect this is gonna be fine. What I don't think is gonna happen is that this second mode is not going to be retrieved because we have only one mode expansion. And I don't see how this intrinsic thermoacoustic mode can be actually recovered. So basically, I'm mostly interested in this first, okay? And this is what happened. So now I was thinking, nice that I understand something from this work, from this model, and I was just playing around. It was, I think it was a couple of years ago, coming back home, a bit tired, but I wanted to play around with MATLAB. And then I did some calculations and I wanted to obtain what I just showed you. With my surprise, I realized that not only small perturbations, but also large perturbations were already accounted pretty well in this small equation. Something that was also surprising is that the intrinsic thermoacoustic mode was also well retrieved, even quantitatively. So it was, oh my god, this is quite mysterious. Why is happening? Why is this thing? And then what happens is that I realized I did a mistake, but it was like a serendipity time, a mistake that makes things much better. And that was basically good news, but it somehow creates a lot of questions that need to be answered. First, why does S square work so well? This is what's going to be the first part of the presentation, and then we will talk about the results. So let's go first with the classical approach. This is the thing I just showed you before. And the novel approach, the difference now is that I have this S square here. In the classical approach, there is no S square. This is going to be a complex number. This is a different complex number. Both of them are obtained from calculations without flames. So this is already quite nice, okay? We have a flame that is described by this model, the flame transfer function multiplied by the velocity, or the acoustic velocity. And now what is the importance or the difference? Here, the difference is, or this is what we just discussed, velocity and pressure are already well mapped with this acoustic impedance. And in this one, we have, by doing some, let's call it reverse engineering, we realize that acoustic velocity should be proportional to something called SP. The question is now, what is SP? Well, we see this map, we will understand this. First, remember that P and U are both complex numbers. So this is actually what we have right now as phasors in the complex plane. If we retrieve this proportionality, we can say that there exists an alpha constant that makes this an equality. And there we can just express S as a complex number, a modulus S and an angle S. Alpha is something that we just tune, but what is important is that U and P are or exhibit an angle difference that is going to be equal to angle S according to this expression, according to the model. Okay, so this is already quite interesting, but before that, let me show you how actual results look like. So actual results, I mean something that comes from a network model, for example. And let's do a numerical experiment. We will introduce an acoustic wave into a duct. We will have a reflection equal to 1, and we will measure the corresponding acoustic pressure and acoustic velocity at the reference plane. Okay? So, for a growth rate equal to 0, which is, so basically the acoustic wave doesn't change in amplitude, we will obtain that the angle between U and P is nothing but P over 2. So basically, there's the well-known quadrature of acoustic and pressure, so 90 degrees, when we have ideal boundary conditions. Okay? Now what happens when we have a growth rate, so the incoming acoustic wave is decaying or growing, we will obtain something like this. Basically, what it tells me, and this is something that maybe not many people is aware about, this is something that it was written actually last year. This quadrature is lost. Now it doesn't exist anymore. We can have angles between 0 and pi depending on the growth rate, depending on the frequency. Okay? So this is the truth. Now, what happens if I introduce this thing that I just found, the model, which is telling me that the phase is just the angle of S, which is just this. If I introduce into the model, nicely, this match quite nice. Okay? And basically what it's telling me is that this model is actually true. Okay? In the paper it's explained that this is actually because we have satisfied the low angle approximation, and some other validation studies are actually shown in the paper. Okay, now that we're interested in that, we will show the difference between the classical approach and the novel approach. We have the classical approach, the novel approach, and importantly, we have the flame model is going to be described by the entire model. It's just something, I mean, for practicity, but we can include other kind of transfer functions if we want. This is also shown in the paper. So, what we see here, we see 3 different tests: Rayleigh 1, Rayleigh 2, BRS combustor, and then we have in the y-axis the sigma, in the x-axis omega, the complex plane, and each point is the eigenfrequency. So what happens if we just focus on in the vicinity of the first acoustic eigenfrequency? We observe we have just this blue line, and when we start increasing n from 0 to 4, then we start making this mode shifting to the right and to the top. So basically we make this mode unstable, and we see that the truth, which is obtained from a network model, is well approximated by this model, the classical approach and the novel approach, actually both of them. But when we go to the other combustors, we see that the actual novel approach does much better, also for high values of n, which is actually 4. Okay. Well, if we do the analysis now on the eta trajectories, we realize that the classical approach actually failed, while the novel approach retrieved these eta trajectories quite nice. Well, we can actually also see what happens in the region of omega 2. Neither classical approach or the novel approach work well, and this is actually clear or understandable because we do just a one-mode expansion. Well, because of that, we go into this 2-mode Galerkin expansion. We want to see what happens, and then we will just, right now we will not talk anymore about the classical approach. We will talk about the novel approach, but with the 2-mode Galerkin expansion and with a simplified version, which means I just do this mathematical treatment to make the characteristic equation much simpler and get this equation. What is nice of this equation, the simplified version, is that it doesn't depend on any parameter of the combustor itself, only on the passive eigenfrequencies S1 and S2 only. So the interest now is to show the comparison of these two with respect to actual reference results. And this is what we see. So we see now that the first acoustic eigenfrequency are well obtained in both novel approaches. Also, the second one is well obtained, as you see, because we now use a two-mode expansion. And also, the eta trajectories, the first and the second eta trajectories, are well recovered. So this is pretty good. Also, has to be clear that the mode expansion, so the complete one, exhibits very, very nice results. Very, very nice results. The simplified version is a bit deteriorated, but it has to be considered that the only parameters of those equation, or that equation, is omega 1 and omega 2. So the two passive eigenfrequencies. And it's surprising that these two passive eigenfrequencies already shape how the acoustic spectrum looks like. Okay, so we go to the takeaway messages first. The nice thing is that we introduce a Galerkin expansion model that actually is based on this assumption that U and P have exhibit an angle of S, so the actual eigenfrequency, and that allows me to formulate such an expression. Okay, and the nice thing is this angle of P and U is valid across different frequencies, and it's different from the one of the impedance, because the one of the impedance is only valid for a certain frequency of interest, and this is the important part. That's why this model is more flexible. And the second part is that we were able to have also a two-mode Galerkin expansion where all this was recovered pretty well. And additionally, if we do a simplification, we obtain an expression that is very simple, but still captures very nicely the spectrum of three different combustors. And I'm pretty sure this has to be exploited in order to, for example, design thermoacoustic similarity, let's say, approaches to understand what happens in actual combustors. Okay. Well, so thank you very much, and well, I will be happy to answer any questions by mail, or yeah, however you can contact me. Thank you very much.